All right, I guess we can get started. Hello, everybody. Good morning. My name is Hande, and I work at the Flemish Institute for Technological Research. And together with my colleagues, Bart and Lisbeth, we'll be hosting today's session on delineating agricultural parcels using deep learning. The agenda will be as follows. So I'll start with a very short introduction on what EO4GEO is. I'll talk a bit about Terrascope and openEO. Then we have a very short poll, which will help us tweak the way we present this webinar. Then my colleague Bart, he will do the actual training, and we'll end up with a Q&A session. So if you have questions during the training, please feel free to use the Q&A box, and we will address them after the training. All right, so let's get started. EO4GEO, what is it? It's an Erasmus Sector Skills Alliance gathering. So apart from VITO, there are 24 partners from 13 European countries. It aims to help bridge the skills gap in the EO and GI sector. The project started in January 2018, and it will in fact finish at the end of this month. But nevertheless, the Alliance will continue to exist. During the project, many resources were developed, so I recommend you to check the website of EO4GEO. There you will find tools such as a body of knowledge, describing the ontology for the EO-GI field, a job offer tool tailored for EO-GI, curriculum design tool, etc. And on top of these tools, EO4GEO offers a wide range of training and training materials. So these are all for free. There's also a mobility program, which is interesting for students, so they can participate in internships that are offered by the companies through EO4GEO. Moving on, I want to talk a bit about Terrascope. So Terrascope is a platform that's developed by VITO, the Flemish Institute for Technological Research, and it's offered also as part of EO4GEO project. So using Terrascope, you have access to a viewer, you have access to virtual machines, Jupyter notebooks, allowing you to process or work on EO data. So these virtual machines and Jupyter notebooks, they have direct access to satellite data that we host. So you don't need to download any data. And we also offer openEO, which is a cloud-based API aiming to work with allowing you to work with data cubes, and it helps simplify the processing of Earth observation data. But my colleague Bart will show you in more detail on how this works and what you can do with it. So we would like to start with a poll that has only 2 questions. Lisbeth, if you can launch it. Like I said, this will help us tweak the way we present this webinar a bit. If majority of the participants are not familiar with some of the concepts, maybe then Bart can modify the way he talks about the concepts. So you should be seeing the poll now. There are 2 questions. The first one is asking about whether you're familiar with the convolutional neural networks. And the second question is whether you're familiar with openEO. So we'll give you 1 or 2 minutes and then we'll see the results. Thank you. All right, thank you very much for answering the poll. So based on the results, majority has heard about convolutional neural networks. And as for openEO, again, half has not heard about it and half half of the participants have heard about it or using it. So which is not bad. So Bart, with this, I will be handing it to you so that you can start sharing your material and tell us about deep learning.
All right, thank you, Hande. Let me share my screen. All right, so my name is Bart. I'm working as kind of a data scientist on the openEO team. So I'm mainly using openEO to implement machine learning, deep learning, and normal data science use cases. This talk will be about delineating agricultural parcels using deep learning. So in fact, we will be using a UNet, but I will be explaining that in more detail later. So what are the learning objectives? Wait, can I get rid of this one? Yeah. So the goal of this training is to teach you like how to perform parcel delineation from like all aspects involved. So basically there are two parts of it. You have the machine learning part in which we will be choosing a model and building a model. And also the computing part. So where do we actually execute this code that we built? So at the end of this training, you will know the basics of even what a UNet is, like even more like standard methods that are used in this field. And yeah, also why this one works pretty well. You will know about what the recent developments in distributed computing. So basically how to execute code in a way in which it is scalable. You will get a little bit familiar with openEO yourself. You will also be able to do actual inference of pre-trained UNet models yourself. So you can actually run this code yourself and do parcel delineation on your own area of interest. And yeah, obviously you will be able to delineate agricultural parcels. So there are a couple of abbreviations that you might hear during or see during this presentation. So data science, like DS, computer science, deep learning, remote sensing. Yeah, so I don't know if I need to explain some of the concepts, but yeah, deep learning is basically like a subfield of data science in which we use neural networks. So remote sensing, I'm assuming that all of you are familiar with remote sensing and Earth observation. Convolutional neural networks is a type of deep learning network. So it's it's basically a subfield, a group of networks within the deep learning field. And the NDVI, the Normalized Difference Vegetation Index, one of the most standard indices that are used within the remote sensing field, and it's one that we will be using ourselves today to do this parcel delineation. So what are we going to talk about in this specific part of the presentation? So we will have a short introduction and why parcel delineation is a useful use case, I guess. Then we will be talking about the machine learning part. So basically talking about edge detection in general, because edge detection is like a very important part of doing field delineation. We will be talking about the deep learning network that we will be using, and we will also be talking about how to pre and post process your data, because that's always in like any machine learning use case you will do. This is a very important part. Then we will be talking a little bit about openEO, and then we will actually dive into the code and also dive into this field delineation use case. So let's start off with the introduction then. So field delineation is useful for a whole variety of reasons. So it's useful for decision making and planning, mainly of provinces, of governmental agencies. But for farmers, it's also a very useful tool for land registration, but also to subscribe for subsidies, etc., to apply for subsidies. Also in scientific purposes, it is useful, especially like it's kind of an input for different kind of physical models. For example, for like if you want to do something with climate change, it can be useful. It can be useful for biodiversity monitoring and modeling. And it's also useful as an input for actual statistical or machine learning models, because it can improve classification results of other applications, such as crop classification. So it can be very useful to know where your parcels are before you actually do crop classification in the first place. So where does field delineation reside in like the wider field of deep learning? And in more specific, to be more specific, in image classification. So actually there are like 4 different types of image classification. You can have this top left use case, which is called image recognition, where you generally label an image with one class. So you will say like, in this image, there is a sheep, for example. Or there is a high probability of there being a sheep. Then you have object detection, which is basically like drawing a bounding box around every object in your image. So this is an object, and this is an object, and this is an object that you detect. Then you have the use case of semantic segmentation, which is just like you will be detecting basically really drawing like really a detailed boundary along the objects that you want to classify. In this case, these are like sheep and dogs, but you're not like separating every instance of sheep. Like this is a group of sheep which are well delineated. But actually field delineation is really this last use case, and this is really the most complex one, where you really want to draw a boundary box, like a very detailed, not a box, actually, like a very detailed delineation along every instance of what you're trying to classify. So that is what we will trying to do. We will be trying to do instance segmentation for this use case. But to do instance segmentation, it is very important to be able to detect edges, because that is basically how how you detect like the boundary of this sheep. So we will be talking a little bit about that. So this is all before deep learning was getting popular. Actually, these kind of methods, such as Roberts cross, there are a lot of like more primitive methods that work on the basis of filters. And Roberts cross, for example, was already developed in 1963 by Lawrence Roberts. And these other filters are like these edge detection filters they are very old. Like also the Sobel filter, I think it was developed in 68 or something, but it was many years ago, and they still work well to this day. They're still used to this day as well, especially a Sobel filter. And how this works is like you have a filter that you run over an image. So that is very similar to how convolution works, but I will be talking about that a little bit later. And you generally have like a couple of filters that are specialized in detecting a certain type of edges. So for example, the Sobel filter, it has 2 filters. So it's like one for detecting vertical edges and one for detecting horizontal edges. And how it works, it's like a 3x3 filter in which you have on the left side, for example, for detecting vertical edges, the left side are negative numbers. The middle side, the middle row is, or the middle column, sorry, is 0, and the right column is positive. So it's basically like enhancing the contrast of your image if you run that over your image. But the problem with these methods is that always it's like a small number of filters. For example, one for detecting vertical edges and one for detecting horizontal edges. And yeah, but these filters are also not trainable. Like they have a fixed set of values, and that might not work for like every single image that might not work for every single image. and also not for like every part within your image even. For example, what these filters are good at is if it's like kind of a homogeneous image in which the color schemes are very similar and the kind of objects in the image are similar. But when you get like more complex use cases, for example, like zoomed in on a flower and on the background there is a building or something, then these methods really start to show their shortcomings. So when we think of like filters and trainable parameters, we generally think of a convolutional neural network if you're familiar with deep learning. Because, yeah, so I will explain a little bit more how convolutional neural networks work. Convolutional neural networks work on the basis of convolution. So convolution is not any different from running a filter along an image. So basically how this works, it's like matrix multiplication between a filter with a set of parameters. And you have your input image and you multiply every value of this image. So you multiply the 0 with the 4, the 0 with the 0, the other 0 with another 0. And you basically add all of these results together. In this case, most of the values in this kernel and this image are actually 0, so you will end up with just 2 times -4, and the final value of this pixel is then -8, and then you will move to the next 3x3 part of your image, a patch of your image, and then that basically you move that along your image until you have calculated like every 3x3 patch of pixels and multiplied it with this kernel. However, and this is how any filter would work. However, the difference between convolution and a normal filter is that the parameters in this filter, in this kernel, in a convolutional neural network are trainable. So these are initialized randomly in a convolutional neural network and are trained as your network basically gets, as you train your network. So how it would generally work in a convolutional neural network, you supply an input image. In this case, it is an input image of a car. You apply a number of convolutional operations that you can set yourself with a certain parameter. And generally that is quite a lot of convolutions, like for example, 64 or something. And that is in contrast to like these two filters that we saw before. And also, like I said, these filters are trainable. So your network will basically find the optimal values for each of these 64 filters that you build in your network, right? So what is then done? So you have a wide number of these convolutional layers, and you apply an activation function such as ReLU to introduce some nonlinearity. This is very important to actually be able to really train your network to detect like more complex features within your network. And then you apply a pooling layer. So what pooling does is it is just, you have different pooling strategies. You have average pooling, you have max pooling, but I will just explain max pooling. You basically, if you have a 2x2 max pooling, you take the maximum value of every 2x2 group of pixels. So in this case, you have 12, 20, 8, and 12, and the maximum value of that is 20. And here the maximum value is 30, etc. If you would have average pooling, then this would be the average of this 4 pixels. And what the use of any pooling strategy is, it is first of all reducing your spatial dimensions, which is speeding up your network significantly, because this is 1/4 of the dimensions that this has. So that's very much of a computational advantage. But also it's kind of increasing the receptive field. And what I mean by that is that this 1 pixel is saying something about a larger group of pixels. So this is kind of like a compressed form of information. And therefore this 1 pixel tells you more than one other pixel in your larger image. Also, it has some other use cases such as noise reduction, but it's not so important for now to go over these details, but that is basically how a convolutional neural network is built up. So you have an input layer, an image, then or a part of an image, and then you apply convolution and an activation function to that. You apply a pooling layer, and that's something you repeat for multiple times. And at the very end of it, you flatten this. So you have like a three-dimensional box basically of yeah, a very small compressed image with a lot of feature maps. So that is like the output of convolution. And you flatten these into like a one-dimensional array, and you connect them to a fully connected layer. And then you apply like another activation function, which is generally like a softmax if you would be doing multi-class classification, if you would have to, if your network would have to learn, is this a car, a truck, a van, a bicycle, a motorcycle, whatever, or a binary classification, then you would have generally sigmoid, in which you would just have, is this a car or is this not a car? So that would be the kind of problems that this network can solve. And I showed this image of VGGNet, which is a more complex convolutional neural network. But the only reason why I'm showing this is that basically it's like any convolutional network is just built up of these basic steps. Like you have some convolutional layers to really apply some kernels which can detect like all sorts of edges and patterns within your image. Then you have a max pooling layer which kind of compresses the information and also makes it easier to calculate, to really calculate this computationally. And at the end you have a fully connected layer and an activation function that transforms like all of these neurons into one single output in case of field delineation, for example, in our case. Because field delineation is kind of a use case, is also a binary problem. So in this case, we could be saying like, is this a car, is this not a car? And we will be saying like, is this a field or is this not a field? And these convolutional neural networks are so good at detecting what is in the image. But what they're not good at is detecting where in the image is it. So you can be detecting like, is this a car, is this not a car? But at the very end of your network, your image looks nothing like your original image. Like this was an RGB image. So this is like a red, green, and blue band of kind of a large image. And at the end, you just have maybe 200 feature maps of like all of these kernels and the outputs of these kernels that you calculate on a very small spatial window. So the first people, so that is basically the problem that we're encountering. So the first people to actually think of like, okay, so how can we actually use this for segmentation purposes? Like how can we use these neural networks for segmentation purposes? Were Sirisan et al. In 2012. And what they did was, their idea was, okay, so a convolutional neural network is very good at detecting what, but not where in the image that what actually is. So can we just do that for like every pixel in this image? And then, because then you would also know where, right? If you know that this is a car or a field, and this is a field, and this is a field, but this is not a field, and this again is a field, then you could like draw your own like boundaries along that, those pixels, along a group of pixels that actually have like the same classified label. And then you could kind of infer like, okay, this is a field, like because all of these images all of these pixels are a field and the rest surrounding it is not a field. However, like what this requires is that you would do inference for every single pixel along your image. And yeah, so this idea like won, and they implemented this and they won a they're actually in the biomedical field. So what they were doing, I think it was like cell delineation or something of like cells. But the problem, so they won this challenge by a large margin. However, as you can imagine, if you need to do inference of a convolutional neural network, like these networks are kind of computationally expensive. And if you would even have like a 200 by 200 pixel image, which is a very small image, you would have to do this 40,000 times. So that's a whole lot of computations that you need to do. So that makes your network slow. That makes it slow, but also, and a second thing is, so that's a huge problem. But the second thing is that, again, you have a very small receptive field. And that is because you need like some environmental information to build your neural network. Because as you saw in this image, like the dimension is like decreasing over time, like spatial dimension. And the power of this neural network is that it's kind of compressing information of a larger area. And it needs this kind of environmental information to really do this prediction. And here, if you do this for every pixel in your image, you will always have like a very, like a limited environment that you can look at. You cannot look at the entire image that you are, that you have. So then Ronneberg et al. In 2015 came with a new idea, and their idea really revolutionized the field of segmentation. It's still used a lot nowadays, and a lot of like newer architectures are built on this idea. And they won the same challenge in 2015 with their implementation of this idea. And what they thought, like, okay, we have a neural network that can do, that can really detect like what is in the image by really compressing the input dimensions. But can we kind of, but like the spatial information gets lost, obviously. And I thought, like, can we build it up, this network, to the same spatial dimension, like the same original dimension that we have, to really get this information about where in the image it is what we're trying to detect, right? So they came up with this architecture. So basically, this is like a standard neural network. This left part of this UNet is just a standard convolutional neural network where you have an input image. You apply a couple of convolutional layers. Then you do max pooling to reduce the spatial dimensions, and at the same time you increase the amount of filters, which are also called kernels, by the way. I think that's maybe important to mention if you are going to read about this. And then again, you do a couple of convolutional steps, and then again, max pooling again. So this is really standard convolutional neural network. But what they then did, they were like building it up again by using up convolution. That was their idea. So what up convolution is basically you up convolution is you have a smaller input and you run again a kernel over it, but instead of like doing normal matrix multiplication, is you multiply like every pixel with these values of this kernel. So for example, here in this case, you'll have 0 times 0, 0 times 1, 0 times 2. So this will all be 0. Then we go to this pixel. So that is 1 times 0, 1 times 1, etc. So that is this one, and then 2 times 0. So that is this part. So, and then at the end, you really add all of these results together, and you have like you have basically increased your image size by doing this operation, right? So that is what they did. And they have a couple of extra things. Like, for example, they noticed that it would be very helpful to have, like, to append the output, like the last convolutional steps, like the feature maps, so the outcomes of the last convolutional step, to the input of that same size part of the up convolution part. So this is the basically, yeah, the convolutional, the down convolution, I guess, and this is the up convolutional part. So they basically append this part of the information, and that will make it easier for the network to really rebuild basically this image. Also, there are some small details to this. For example, they're using valid padding. So maybe, yeah, as you can see, like in general, if you do convolution, you will always need your input image always shrinks with like 1 pixel around the entire image, because here, for example, for this pixel, you don't have a top row to really calculate this kernel width. So the first pixel that you can actually calculate is this one, and then that one, and all the other pixels you can calculate that are within that, but the outer row is, you cannot do that with normal matrix multiplication. So what many people do is they use padding. That is done here as well. So you pad like a 0 around it, and then you can actually do matrix multiplication. Then this would be your original image. But in this paper, they decided not to actually do that. So the input dimensions shrink, and that's why the output image is actually a little bit smaller than the input image. Because that's happening like every time you do convolution, right? So yeah, so that is something they, so what they then did was they took like a crop of this output layer to really match these input dimensions. Yeah, so what they did was to circumvent this a little bit, to be able to classify an entire image. Because yeah, as you can then see, you have an input image of like 570 by 572, and then the output image is 388 by 388. So you need like a larger part, a larger image to really classify the smaller part of the image. And for that, they use like a mirroring strategy. So as you can see, this is like mirrored, these kind of features, you can see them here. And this feature, you can see them here as well. So it's really like a mirror. Yeah, it's mirrored. Yeah, so what we did was we used kind of a simplified version of this UNet. So we didn't do this. One of the things that we did was we actually used padding so that the input dimensions and the output dimensions would be equal. That makes it already a lot easier. Also, we used a sigmoid function instead of softmax, as we're doing binary classification. So we're basically determining, is this a field or is this not a field, right? We used the padding. I already said that, and we have a different set of output and input dimensions. Also, we added batch normalization. I think that's not too important for now, especially as I saw that a couple of people are not familiar with convolutional networks yet. So it might, I think this is already a very, it's already a very intensive introduction, I guess, for you guys, for the people who haven't heard about CNNs yet. Yeah, so this is the final architecture that we're using. So it's, we use padding. So then the output dimension and the input dimensions are similar. So that is what we're going to do. So this was more like the machine learning part. Now we will be really going more into really this use case already, very tailored towards this use case, because Earth observation data is a little bit different than like a standard image. So most of these techniques have been developed on photos, right? So they have an RGB channel, so that is red, green, and blue, and they have a certain height and a width. And they definitely don't have any temporal dimensions, right? You will be, that's something very specific to to satellite data, I guess. So Earth observation has more bands, so you might have an infrared band or yeah, something else. And then also, yeah, we have an extra temporal dimension. And it would be a shame if you cannot make use of that data, because in the end, like the more data you're able to incorporate in your network, generally, like the better your chances of getting a good model would be. Like the input data is super important. So we decided to compress the NDVI band, like this band dimension, into basically one dimension by calculating the NDVI. And also to make use of this temporal dimension, we pass 3 different temporal snapshots. So what we're actually going to do is what you generally would have is you would have an RGB band, like a red band, a green band, a blue band. And what we will be passing is an NDVI snapshot of maybe January, one of February, and one of March, or something like that. And that, yeah, that we will train our model using that. Also, yeah, how we choose these temporal snapshots, so the actual dates, are based on the amount of cloud affected pixels they contain. So as you can imagine, if you want to do field delineation, but you have clouds, then that's going to be very hard. So we are choosing the NDVI snapshots that have no clouds whatsoever, or at least the least amount in the temporal period that we supply. And also we clamp the data, so basically remove like the very top and the very bottom part, as they can also be cloud affected. And also we rescale it. That is also important for a network. I think in any machine learning use case, like proper pre-processing of your data is super important. But also we do some post-processing. So at the end of a UNet, this is what we actually get. We will see that later when we dive into the code. So this is before applying a sigmoid. So this is like a continuous output without having actually done this binary classification of this is a field and this is not a field. However, it is an instance segmentation like a network, right? So we'll it's not like delineating. It's basically delineating, is this a field or is this not a field, but it's not delineating every instance of a field. So what we're actually going to do is we take this output before applying a sigmoid, before converting them into like a binary map. We apply some extra filters. So we're actually going to apply some old school filters, such as Sobel filter, and to actually improve this contrast even further. And then we will use RAG boundary analysis to convert them into instance segments. So what RAG boundary analysis, so that is a region adjacency graph. And what it actually does is it makes nodes and vertices representing regions and edges. And these regions can then be merged later on. So what it does is you have an original image. Then using this RAG boundary analysis, you have this kind of like nodes, vertices kind of pattern that you get. And you can merge these together based on a certain threshold. And as you can see, this will be creating like distinct regions within your image. And these, by converting these to a raster later on, you will get very clear, like distinct boundaries. And you can play a little bit with this threshold to really make these, like more boundaries or less boundaries depending on your specific use case. So that was yeah, that was useful for us. This concludes basically the machine learning part of this demo, or at least in a theoretical sense. So let's move into the actual field delineation part by choosing a platform. So we need to actually write code, obviously, to really transform this like theoretical idea of like, okay, we're going to build a UNet, which is based on like a couple of convolutional, a standard convolutional network and an up-convoluted part that is appended to that network. And also basically we need to do a whole lot of pre and post processing. We need to actually access satellite data, obviously, to actually calculate this NDVI that we will be using as an input. So those are also all sorts of decisions that we need to make. So we will be talking a little bit about how why we chose openEO. Also how, like different ways in which this kind of computation was done in the past. And then, after that, we will actually dive into the specific use case. So traditionally, I took this image from like a bioinformatics field. But like the Earth observation field is not really any different from like any other field in this perspective, and in the perspective of how computing has evolved in the past. So in the past, you would be downloading data locally, like you would be downloading satellite data also locally for the specific tiles that you would be needing. You would be storing them locally, do your computation locally, and then you would upload your data to repositories for publishing, right? So you publish your data afterwards. However, like the problem with this workflow is that it's not very scalable. Like if you need, this would be a very good approach if you would be have to do something on a maybe 100 by 100 kilometer bounding box or something. That would be possible. However, if you want to do like a European project or something and have to do inference for like a very large area, that is going to be very challenging to do that. So then basically cloud providers came into the picture, where the idea was like, okay, we move the processing to the data. So a lot of cloud providers emerged, which would be offering their own processing capabilities for you, and also their own maybe even like entire pipeline of machine learning stuff that you could be doing on them, depending on like the cloud provider. And what is currently the case is that you have a lot of different cloud providers. You may have an Amazon, the AWS, a lot of different cloud providers, even in the Earth observation world. And all of these providers have their own clients, their own way of like interacting with their backends specifically. And you kind of as a user become like an expert in that specific backend. Like you may become an AWS expert and be really familiar with, how to do your processing on that specific backend. But then again, the problem is like if you need to move to another backend for whatever reason, that will be very hard for you, because you will have to, first of all, learn how to work with that backend, but also you will basically have to move like all of your projects and probably rewrite a very large part of your workflow. And that is something that openEO tries to solve. So what openEO, the idea of openEO is that it constructs an API that connects a unified client interface within Python, JavaScript, R. We also have a web browser, to big Earth observation cloud backends in a simple and unified way. So the idea is that you can connect really to different backends using like one unified language. If you decide to use Python, then you can use a Python client, and you will be able to connect to different backends using that one Python client language. I included some links throughout this presentation, by the way. So if you really want to dive into different things that you can do that afterwards, and really explore things in your own, in maybe more time than the 2 hours that we have. So this is, yeah, the idea. There's a web browser, there's a Python browser client, an R client. They all send basically your requests to different backends, and you might not even be knowing what backend you are computing things on. You might also, you have the option to really select one, or you have the option that we select one for you, depending on what is available on the backend and what kind of computing resources are available there at the moment. What openEO also does is data harmonization. So basically, the collection names are different on every single backend that you are processing on. For example, if you would be processing on Creo.is, Sentinel-1 collection would be called Sentinel-1. If we'll be doing it on Sentinel Hub, it will be Sentinel-1 GRD. And through openEO Cloud, you would have one unified collection name, so that you do not even need to like think about changing those if you move to a different backend. And how it actually works is you have a simplified client language. This is just a stupid example, but generally you would have a lot of more complex operations, obviously, like loading collections, masking collections, and whatever. But this is just a simplified example to see how it works. What the openEO client does is it transforms your request into what we call process graph, which is a JSON representation of this operation that you are trying to perform. And this process graph is implemented by all of the backends. So all of the backends learn to recognize this process graph and implement it in their specific way. So for example, the Terrascope backend that Hande talked about before is using a GeoTrellis stack. So and the data distribution is done using Spark. So that is, or the implementation is done in Scala. So that is like one way of doing it. And then, for example, the EUDC backend is based on Dask, which is built using Python. So that's like a completely different backend, implementing things in a different way, parallelizing your requests in a different way. But the syntax of like talking to these backends is the same. And openEO works using data cubes. So that is just a representation that is very useful for dealing with satellite data. So basically, you have a spatial dimension, your X and your Y. You have different bands depending on the sensor that you're using. So a red band, a green band, a near infrared band, a SWIR band, like whatever sensor and that you're using. And you have a temporal dimension depending on the time period that you select. So that's like a 4-dimensional representation that you can access using data cubes. So that is more about more of a very theoretical workflow of what openEO can do, but let's talk about a little bit more in detail what kind of operations can you actually do with openEO. So I formatted this in basically a machine learning workflow, and what a machine learning workflow would generally look like. I mean, generally a machine learning workflow would have like a kind of a circular process where you have like a feedback loop. But this one was very simple, and that's why I took it. So basically you have a data part, you have a feature selection, like pre-processing basically your features for giving them to your model. Then you have a modeling part, and you have an evaluation part of how well is your model actually performing. So the data part, in openEO, there are a lot of collections available. I said here 76, but I think this amount is like growing literally every week. Like more and more collections are becoming available that you can use, and most popular collections are already available there. You can check them out here and really also browse through things that you might be needing. Yeah, so that is something useful for let's see, how can I get back to my presentation? Yeah, okay. Yeah, there are a couple of ones coming up still as well. I think world cover is already implemented. So yeah, you can check that out yourself. But then maybe a more important part of like how to pre-process data, what kind of things that and kind of feature selection operations that you can do. So first of all, with respect to pre-processing, you can mask your data, for example, applying different cloud masks to your collections. You can filter your data, like filter on bands, filter in the temporal dimension, filter spatial dimension as well, onto different areas that you're really interested in. You can do band math, so you can calculate a different number of indices. For example, you can aggregate over temporal periods to really get like yeah, to get like for example, taking the maximum over a space over like of all the dates that you selected. You can also aggregate spatially to get like a time series. So you will have like a certain area for which you have maybe certain features, like a certain index that you calculated or something, and then you aggregate them spatially to really get like only the spatial the temporal changes over time over that area. You can merge cubes. For example, if you have Sentinel-1 data and you have Sentinel-2 data, and you calculate some features over them and you want to merge them together, that's possible. Then you will need, by the way, resampling because they have a different spatial resolution. So that's something that you can do as well. You can also rescale your data. That is, for example, for computational purposes, that is useful. You can apply functions along different dimensions, for example, the temporal or the band dimension. This will be very useful also when doing machine learning. You can calculate a number of indices. So we have a number of ways to do that. I will come back to that later. So you can do that using band math, but we also have a lot of indices directly implemented already. And that is even easier and faster also. And also you can do feature sampling. So for example, you might have reference data for a certain area, for certain areas. So you will load in a large collection, but only needs your features for those specific points for which you have reference data. So you can actually extract those features in those points and download them locally. Also here, there's like a large list of all the processes that are supported. So there are a lot more than I can actually talk about at this point. Yeah. So then we get to this modeling and the evaluation of your model part. So actually, most of the time we model outside of openEO. So basically, what we do is we load a collection, we do the pre-processing, we calculate a number of features. For example, we might calculate a number of indices, and then of those indices, we might calculate a standard deviation and some percentiles, and maybe extract some temporal steps, like some temporal snapshots to really train our model. Then we extract those features into the points for which we have reference data. So we have a reference set and we download just the feature set for that specific reference set. And that, like, I mean, model training, then we will do our model training locally, because like model training is generally not so computationally expensive, especially if you're not doing deep learning. Then model training is not so expensive in the Earth observation field, like, right? Because you might have even if you would be training a model like on a European scale, you might be using 30, 40, 50,000 reference points to really train your model. So that can be like a simple CSV file that you store on your computer, which is not even like yeah, 1 GB or something. It can be very small, right? But obviously the heavy part, the heavy lifting of doing this Earth observation machine learning part is like applying your model on large areas, because then you will need to do the inference you will actually need to do on a European scale if you're creating a European model. So then you will need to do inference for every pixel on a European content. That is like very challenging. And for that, we will be using openEO again then. Yeah, and also openEO, like the backends that we have for now, do not support GPUs. So even if you would be using deep learning or training convolutional neural networks, you would not be doing that quickest on openEO, because our infrastructure is just not at this point like supporting GPUs. It is something that will be happening in the future, but not at this time. So like I said, at the end, we will be doing inference using UDFs. So a UDF is a user-defined function. So that is basically, you can write any custom code, like normal Python code that you would be like running locally, and we will execute it on a backend. So we have different ways of doing that. You can apply a process to every pixel. You can apply a process to all pixels along a dimension without changing cardinality. So that would be apply dimension. That would be generally something you would do when doing machine learning, right? Or reduce dimensions. So you would be maybe having a whole bunch of features along a band dimension, and then basically compress them all to a single prediction for that pixel. Like this is a car, or this is this is I don't know, this is a crop, or this is a certain type of crop in the machine in the openEO work field. And then you can also apply a process to all pixels in a multidimensional neighborhood. So that is basically applying a filter along an image, and that is what we will be actually using, and that is called apply neighborhood. So for parcel delineation, that is something we will be using, and we will get to that later. Modeling in openEO. So we can actually model in openEO. We do support some basic modeling. However, at the moment, we only support random forest and cat boost. But the problem with this still is that, I mean, for these models, you will not need to actually do it in openEO. I mean, I can train a random forest model like on maybe 40,000 samples in like half an hour or something. And also I would have like maybe an hour or a couple of hours, but it's very fast. And you have like all like the sklearn and all these packages available with all the functionality that they offer that we do not yet offer within openEO. So things like grid search, random search, like different ways of tuning hyperparameters are just not supported in openEO at the moment. So that's why it's still likely faster to use, to really use this previous method of like loading a collection, doing all of your pre-processing and calculating your features, then extracting that out of openEO and applying it again after you train your model in openEO. So then the final inference, I already said a little bit how we're going to do that. So that's using UDFs. So yeah, I am not going to go into a lot of detail because we will see this when we dive into the code a little bit. But you can read about that yourself if you're interested. So a summary of a workflow that we recommend is like you do your data loading and your data pre-processing and your feature engineering within openEO. You extract the samples for which you have reference data using filter spatial. You model outside of openEO in your own environment, or maybe, where you might have access to GPUs and whatever. And you apply your model again using a UDF to do the inference. So let's dive a little bit into the practical side of openEO to show you how it actually looks like. We have a lot of documentation available that you can have a look at if you're interested. So you can install openEO easily in the Python client. Yeah, maybe I should mention that before. This I should have mentioned those at the very beginning. But we are actually, in this presentation, I'm talking about the Python client. It's also the client that I'm using at the moment, and it's the client that is most well supported, I guess, also. But we have an R client as well, and you can use that. But this presentation, also this implementation, is in Python. So we can install Python easily using pip, and then import it in, if you start a notebook or a general Python file using import openEO. By the way, I see already some questions popping in. I'm not sure if I might answer them at the very end. I cannot see them here, by the way. Yeah, we will have time for answering all of your questions at the end. Yeah, so that's basically how you import openEO. So import openEO, then the first thing you do is you make a connection to either a specific backend or our aggregator. So that is openEO.cloud will send you to whatever backend it deems suitable at that time, depending on like what kind of operations that you are trying to perform, and also, yeah, also basically the computing resources that are available. But you can also connect to a specific backend. For example, if you would be connecting to the VITO backend, to Terrascope, you would be connecting to openeo.vito.be. And then you would be really sure that you're talking to this VITO backend and only making use of VITO features. Also, then after that, you can load a collection. The first thing you supply is a collection name. Yeah, I already showed you this overview of like all collections. This is also where you would look up like the actual collection that you need. For this one is, for example, yeah, that's basically this one that we're using. So here you can find the collection name and also, yeah, like for which time range the data is available. So you have some metadata on like for which dates and also which bands are actually available. So this is also something you might want to use. So what we can also do is we can already specify like a bounding box for which we actually want to load in the data. We can supply like a temporal extent for which we want to load in this data, and also the bands that we actually need. Yeah, so that is that. Then we have some data, right? So what we if you want to, but that data is still like, it's not actually executed on any backend yet, right? So until you actually start a job, either a synchronous job or a batch job, your code is not executed. It will be tested, like whether it's valid code by the client, but like before, like this code still needs to be sent to one of the backends, right? And you can do this in two different ways. So you have synchronous jobs, which are like, which do your calculation immediately without like putting you in a queue or something. But it's like, it's fast calculations, but you can only do very small areas. So you can do a small area with like a restricted time. And if your job takes more than 15 minutes, it will definitely not run. So if you would be doing anything heavy, any heavy calculations, or doing something over a large temporal range or a large area, you will not be able to use this, because then you will be using batch jobs. So batch jobs work using a queue. So you will be getting status updates regularly, like every minute, I think. Over a large, yeah, so that you can use, basically, you can do any sort of operation over very large areas as well. And this is how a synchronous job looks like. So that is basically on a data cube calling download. with a certain file name and a certain format, like do you want a net CDF or a GeoTIFF, for example. And batch jobs look like this. So you have different ways of doing starting a batch job. Execute batch gives you like regular status updates. So basically your kernel will be giving you status updates all the time, like every minute or something. But that also means that you cannot really continue your coding process. But that's why we also have send job or create job. And then this just starts a job on a backend, but it will not regularly give you status updates. So that's something you will need to do then yourself, like ask for the status every now and then until your job is finished. And that seeing whether your job is finished, you can see by calling the status command on your job. Yeah, I talked about filtering a little bit before. So we have 3 different types of filters. You can filter your cube temporally. So these are like different temporal time steps in which you have a snapshot available. And then, yeah, you select one of them. You can also select bands. For example, I only want a near-infrared band, and I can only select like a certain spatial area. In practice, this looks like this. You call like filter temporal on your cube. You can call band on your cube, and you can call filter bbox on your cube. Band math. So you can filter on these bands like I showed here. So you can call like band on your cube. And store them in a variable. For example, this is band 4, band 8, and then we can use these variables to do actual band math. So that's very intuitive. But that's one way of calculating indices, but actually we have a couple of ways of doing that. The fastest way is to calculate indices using compute indices or compute index. We have 3 different methods. You have compute index, compute indices, and compute and rescale indices. I have an overview of the indexes that you can actually, the indices that you can actually calculate, and also yeah, the more detailed explanation of how these work. But basically, compute index just expects a string as an input, so just NDVI, for example. Compute indices expects a list of indices, and compute and rescale indices can also rescale your indices afterwards. You can also apply like different operations, such as like taking the absolute value of like every pixel along your image. This is something we will be using as well for applying our UDFs. And yeah, we will see that a little bit later. This is kind of complex, so it's also, yeah, it's something you might need to read upon yourself a little bit to get really more familiar with this. So there are different ways of like passing something to either one of these apply methods. You can apply like a certain function that we already integrated, for example, taking the maximum value. You can also write like your own function and supply that one to this reduce dimension or apply dimension or apply neighborhood method. So yeah, let's dive a little bit into some code. I think the first one is this basics notebook. So yeah, basically this is basically how you can find this notebook, by the way, in the same GitHub repository as the slides are. So that's on the GitHub page of EO4GEO, and then VITO parcel delineation. That's how you can find the presentation back, and also the notebooks. We import openEO, and we make a connection to a certain backend. So the first time that you will do this, you will get prompted with a authentication procedure by by EGI actually. And you can connect to them using like your social logins. So if you are connected to any university, for example, or a research institute, and you will be able to connect via EGI. Then we can load in a collection. And this collection, like I said, as you can see, this is like loading, this is executing immediately. And that's because like none of the data has actually been loaded until I actually start my job. So until I actually start like downloading this, for example, here, I will actually download the cube that I have, actually the maximum value along the temporal dimension. And then it starts actually loading my data. And yeah, this was a fairly small job as I selected like a fairly small area with a small like temporal extent. So this one finished already, and we can then inspect them if we actually if we actually look at them in, for example, in QGIS or something. I haven't done any cloud masking, so this will not like if I take like the maximum value along the temporal dimension on a non-cloud masked image, then I will probably get just clouds. So this is not like a, so generally you would be doing cloud masking first. We can also calculate indices. For example, I can calculate the NDVI, and this time I will be using a batch job. And in this case, I used execute batch. So this one gives me like status updates all the time, but it will also keep my kernel busy, so I cannot actually start new jobs while I'm doing that. However, that's why we also, like I said, we have also send job or create job, where you can just start your job with, and are able basically to continue like executing cells in the meantime. And you can then ask for your job status using job.status. So there are a lot of like some other things here that might be useful for you that we also saw in a presentation already. But yeah, I'm not going over them at this point, as we are a little bit short on time, I think, already, because we need to also look at the use case, obviously, of parcel delineation. So how do I get out of this? Yeah, so this is the parcel delineation use case. I might actually start it myself also here in my local environment. So first of all, this this whole use case that I've been talking about was not developed by me. It was developed by Christophe van Tricht and Jeroen Dries. So Christophe actually built the models outside of openEO. These UNet models, and Jeroen actually did this whole transformation to openEO and made this. It's just me and a colleague. We helped with tuning, and I'm just telling the story also about this use case, and because it's just a useful use case for people to learn about. So first wait, do I have this? This should be, wait, I need to look at this folder structure. Oh, wait, where do I have this? It's I think I'm missing a folder here. I will actually be starting it with another, or will I even need load UDF, by the way? Yeah, I will be needing it. Yeah, I can quickly, yeah, maybe it's not too important for now. I will fix this for you guys because that's I should have run this from this repository before. I do think I can find another repository that I will have this method available. Yeah, okay, I'm not going to fix this now. I think this is not too useful for you to see me guys debugging this one import, but basically this import is missing. So yeah, I will fix that import for you guys so you can actually run this code. But I supplied a lot of images along the way as well, so that is that will be okay. So we again connect to a backend, to a certain backend. So in this case, we're again connecting to this aggregator, but I can also connect to a specific backend, for example, openEO.vito.be. And then we supply just some features that we will be using later on. So we will be supplying a certain bounding box and the year for which we actually want to run our inference. And we select a certain time period for which we can actually select these NDVI images. So then we can actually start loading in a collection. So we load the Sentinel-2 data set because it has like a nice spatial resolution, but also it's available globally. So that is like, that's very useful for this specific use case. And we will be applying a cloud mask. So this is a process that is supplied by VITO. It's based on Cent2Core. But it's a modification on it. Yeah, but you can apply whatever masking procedure that is useful for you. We have a couple of examples of how to do different types of cloud masking as well. So I think they're present in the presentation. So you can check them out yourself. Then we calculate the NDVI. So we have actually another method to calculate this index, and that's because the NDVI is just so popular. We could have also used this compute index function to actually calculate this. But yeah, these are different options that basically you can use. Then we can apply this UDF to actually start the first thing that we want to do. So the first thing that we actually wanted to do is we want to reduce the amount of images, because as you can imagine, we're now selecting like the 1st of January to the 30th of September. And those are a lot of images. So we will have a lot of NDVI images. And in the end, for this model, we will only be using 12. Why we're using 12 is because we actually have, we are going to select like random, the input is of the UNet is 3 NDVI tiles, right? So that's something I explained a little bit earlier when we were talking about this machine learning part and the pre-processing that we're doing. So this UNet is going to take a 3 by height by width input, and we are going to supply 3 NDVI images, snapshots. So 3 like temporal snapshots of NDVI. However, we're going to run the model a couple of times and like supply like different NDVI images and take the median of all of those calculated outputs. That will help us to like combat like any noise or like any specific details that you might see in one specific temporal snapshot by having different predictions. And how this reduce images works and how maybe also a UDF in general works a little bit is like I said, you just have like general Python code, that is this one, and you're working with an X array, right? So because that's what you get. So when you apply a data cube along a dimension, you can get the actual array for that pixel using the method getArray. And that you just have an X array that you can do like any normal operation on that you would be doing normally. So in this case, we're sorting this array on the amount of clear pixels that each of these arrays contain. And basically we return that, right? So we return basically the image with which contain the images which contain like the least amount of cloud effect pixels, and we contain 12 of them. We return 12 of them. But to apply UDF, we basically wrap this whole method into an apply data cube in a different file, and we supply that file to apply dimension. That's how it works. We can apply this to two different dimensions. So in this case, we're applying this to the temporal dimension, right? And this is what these three images look like. So we have just three NVI tiles which contain very few clouds. So these are few clouds. The least clouds, at least in this specific year, in this specific time range that I supplied. And then we can actually start doing the actual segmentation. So we start looking at this actual UNet. So again, this is going to start from this apply data cube methods that we have defined, and we get a data cube. So that is just our 12, that will be our 12 NDVI tiles that contain the least amount of clouds between this specific time period that we selected, which was the 1st of January to the 30th of September. What we do with this is we basically clamp the NDVI values, and also we rescale them. And what we then do is we split basically our none values. We store them in a separate file, which we call a mask. And we supply that mask with our NDVI tiles to the process window method together with our models. So what our models are pre-trained. So Christoph actually pre-trained these models already. And I stored them on my Terrascope directory. And like I said, we have three different models. So we have two different ways of like decreasing noise and like increasing our final result, which is we have different models. We have a couple of models which give us all give us like a slightly different output. And also we can select between these 12 input images, 3 images to put into these networks. So that's what we're going to do here then in this process window function. So we load in the models, the mask, and this NDVI cube, data cube. And then, which is then, by the way, is not a data cube, it's just an X-array. We mask the NDVI data. And then what we're going to do is we sort the data on the amount of clouds, basically. So what we're going to do is we're going to look at if there are images which contain no clouds at all, and if these images are like, if there are more than 3 images which are completely cloud-free, then we will just be using all of the cloud-free images that we got, because in the end, like, we want to use more NDVI tiles, but at the same time, if they contain like more clouds, then it's not going to be beneficial for our final results. So we're just going to try to see if we can find 3 images that are completely clear, like, you have no clouds at all. And if not, then we will be using at least like the 3 best images that we can find. What we're then going to do is we're going to do 12 predictions. So what we're going to do is we're going to use these 3 different networks that were pre-trained. And for every network, we're going to train, we're going to do inference 4 different times, because we might have 12 like NDVI snapshots. We will, and yeah, if in case they're all 12 of them are cloud free, then we will want to use all of them. And in the end, we then have these 12 different outputs, and we just take the median prediction of all of these 12 outputs. So that's basically how this UNet works. And then at the very end of that this is your result. This is what we will have. So this is at the very end of doing this, applying this UNet, before applying a sigmoid to really binarize, take like the binary result of the network. So then, yeah, as I explained before, we're going to do some post-processing. So we're going to do apply some extra edge detectors to really increase this contrast even further, and then use rack boundary analysis to really convert them into instance segments. So how this works is these are also filters, by the way. So we again use apply neighborhood. I didn't say this before, but this is also with this segmentation. This is convolution, right? So you will be running a filter along an image. And in this case, we can supply both basically the step size, which is like how much overlap every image will, like every patch of pixels that you will analyze has, and also the size of like the core, the step size of like what your the unique pixels that you're basically supplying to your network every time. So what this actually does, so we have a network that accepts like a 128 by 128 input. So this is 64 plus an overlap of 32 on both sides. So that way we end up with a total window size of 128. And with these Sobel and Felsen-Schwab filter, we take a little bit of a bigger window, a 265 window, without any overlap. So yeah, that's what we're doing. And yeah, I explained this already quite a bit. So we get our array, and so we have then an X array. We apply Sobel filter and the Felsen-Schwab filter, and we perform this rack boundary analysis and use this cut threshold to really convert all of these like partial wait, where was I? Yeah, to basically convert these nodes and edges that we have into really like homogeneous fields or classes. And this can be just tuned to like your specific use case. Although this works pretty well for the areas that we did this field delineation on. Yeah, and then you will have this will be the output of this analysis. You can already see really clear like this fields appearing. And then the only thing we're going to do then is to convert it to from a raster to a vector to really get these discrete fields. And we can then also plot that actually, and this is your final result that you will then have. Yeah, so I think, no, wait. Yeah, so I think that was it from my part for now. we still have a room for questions, and I think Hande will also be doing an outro. So if you have any questions, then please contact us on our forum. openEO has a forum where people can ask like specific questions about openEO itself, but also about specific use cases, and we try very hard to really reply rapidly to all of your questions related to openEO and the use cases that you're doing. You can also suggest new things for us to implement. If you have a use case and you need a certain functionality that is not implemented yet, then let us know and we will try to accommodate for that as well. Yeah, so thank you for your attention.
Thank you, Bart. I will be sharing my slide, but in the meantime, there are 2 questions in the chat. So the first question is, in which way differ the 3 pre-trained networks simply using different training data? That's the first question.
I think there is also a slight difference in tuning, but if you want like full details, I can supply you with the contact of Christoph, who actually built these models himself. So I had a look at the code, but yeah, I think it's best if I will contact you with his email address, so you can actually
all right,
ask him about more details about that.
Okay, and there was one more question. Lisbeth, I lost my chat window, so if you could, or Bart, you can maybe see it yourself in the chat window. There is one more question.
Yeah, so have you done any systematic accuracy evaluation yet? Yeah, evaluation was done. It's always a little bit challenging with field delineation in particular, because obviously you have like, you can determine like how well, how do you say that? Like, for example, if a field is cut up into 2, then how do you determine like how close a field is to your actual reference data? But that's like a question, like that's a challenge in basically the segmentation field in general. But there was evaluation was done, and I don't have the results here on my laptop, but also that is something that Christoph can provide you with. So yeah, I will, maybe you can give me your email address and then I can, yeah, put you guys in contact really.
Right, so we probably have Felix's address through the registration form, right, Lisbeth? We could send a mail to him. Are there any other questions? I see one more. Thank you. You're welcome. So this training material and the recording of the webinar, it will be available on the EO4GEO website. It's not there yet. So I sent the direct links. I put them in the chat window. If you want to see them immediately, you can reach through that, through those links. And like we said, Bart will be fixing the notebook so that it is runnable or executable. You could use Terrascope notebooks to run these notebooks, so you don't have to install anything extra. You could use your own Edugain account, or if you have EGI checking, you can just log in with those credentials. You don't even have to register. Or if you don't, you can register to terrascope.be and you can access to those notebooks as well, or the notebook execution environment, as well as openEO. We do have an evaluation form. If you have time, you can access to the form through this link or through the QR code, so you can take a screenshot, and maybe when you have time, you can fill it in. It would help us to evaluate or see how our webinar was. And if there are no more questions, we will end it here. If you come up with other questions after the webinar, feel free to reach us. You can reach Bart through his email address, bart.riesen@vito.be. And you can for sure ask him your questions. I will wait another minute for questions. I see none. All right, then that means we are finished. Thank you very much for your time, and hope to see you all again. Thank you. There's okay. Thank you. Welcome. Thank you.